Okay, so this is the second part, second video. It's looking at Chapter 1. Okay, so this is where we left off in the last video with the Andromeda Galaxy 2.537 million light years away. That was like, we had the other ones here just as a reminder. Sirius, the dog star, is 8.6 light years away. What that means is that the light you're looking at there started here 8.6 years ago. So you can remember what you're doing 8.6 years ago. That's when this light that we see from Sirius coming to us started towards us from the surface of Sirius. And so on down the line, we had Polaris 433 light years away, Betelgeuse 642.5 light years away, and then there's the Andromeda Galaxy. Here we have how old is the universe. The Big Bang took place about 13.8 billion years ago. Stars started to form when the universe was only about 200 million years old. Okay? Many stars went supernova, giving us all the elements heavier than hydrogen and helium that were synthesized at their cores. Our sun formed about 4.6 billion years ago. So stars started to form when the universe was only about 200 million years old. So obviously that's right around, not that far from when the Big Bang took place. But our sun is very, very young compared to the overall age of the universe. And here's a interesting little graph. Basically, this is where the Big Bang happened. Just words like inflation, quantum fluctuation or fluctuations, afterglow light pattern, and all that. That's the Big Bang right there. And this is time going forward. So this is where we are right here. And so the first stars are about to form for about 400 million years, 200 million years, whatever. Dark ages is not the dark ages on Earth. Earth does not exist yet. Neither does the sun. Okay, so development of galaxies and planets, etc. is happening in here. Dark energy, acceleration, expansion. But the Earth and sun only come about right in this place right here. Okay, so in your book, okay, we're basically here. Here's the planets and their distance from the sun. Mercury's the closest. Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The asteroid belt would be right about here between Jupiter and Mars, in between Jupiter and Mars. Okay, what I was looking for in your book, I don't see it. Okay, it's got to be in a different section. Hold on a second. So anyway, we can see there's the spiral galaxy. This one looks like, we think, the Milky Way. We're pretty sure the Milky Way looks like the Milky Way. Okay, it's thought to be similar to our Milky Way galaxy. So this is, we're able to get far enough away. This is what we think the galaxy we live in, a collection of gravitationally attached stars, billions of them. Okay, so there's a whole other galaxy. It's like ours. Okay, and then this would be the Milky Way. If you got to be very, very dark. Where we are in Sacramento, you can't see the Milky Way. It looks like a big cloud, but the cloud just kind of stays in the same place all night you're looking at, or it moves just a little bit, and you think, why is the cloud not moving more? Because it's not the cloud. It's the Milky Way. It looks continuous, but it's billions of stars you're looking at, like little pixels that make it look continuous, like little pixels on a computer screen that makes it look continuous. Okay, and you get somebody standing out. Look, the sun just set. The sun just set. Man, that is a really good shot of getting the Milky Way. Let me even tell you where this is. California desert. Hey, we could do a field trip there if we didn't have the COVID thing going on. Okay, so what am I looking for? This is a star cluster, a blue star cluster, and let me do this now. Okay, I've skipped down. We'll go back and do 1.7 and 1.8. I've skipped down to 1.9 because this is what I was looking for. I thought it was in that section there, but I was wrong. Okay, but basically, this is saying, what if we were to kind of increase a calendar that we're used to give us an idea of when things happened at what point they happen. So this is all the months. Okay, they got November here, and then they go into December right here. So January 1st, that's when the Big Bang happens. Okay, February is when we start to form stars. Maybe the stars become a little bit more organized. We start to form galaxies. You see the blue and the red. That's all star formation. The Milky Way galaxy forms in May. Okay, so you got January, February, March, April. Finally, in May, the Milky Way galaxy would have formed. Then June, July, just more evolution of the solar system. As time goes by, you have the big, huge, massive stars. They are enormous, and they basically, to survive, they're fusing hydrogen into helium. Then they run out of hydrogen. They fuse helium into carbon and other elements. All the elements on the periodic table are coming from the inside of stars, except hydrogen and helium. But all the Golden Sierra came from the inside of a star that blew up. It blows up. It's blowing up in here someplace. And as it blows up, it spews out all the elements: carbon, oxygen, gold, silver, titanium. All those elements are getting spewed out into space, and they become a big cloud. And the big cloud, so here we got, so this is where the solar system begins to form. So someplace in here, some star blew up, sent out all these ingredients that would become the big cloud that would start to form our solar system. A big cloud made up of all the elements. Earth's atmosphere starts to form in October, and then first complex life forms appear in November, and then we go down to December. More specifically, vertebrates appear. I think that means they have backbones, right? Land planets appear. Okay, dinosaurs appear. Okay, so here we're talking about the Big Bang happening here, beginning in January. Dinosaurs don't come about until December 25th. And then mammals appear. And then, boom, dinosaurs become extinct. Humans appear on the 31st of December. Okay. So that kind of goes along with this. Okay. Big Bang and all the stuff we're used to, we see around us, happened up here. I mean, even the Milky Way galaxy, okay, that's forming here. Okay, we're almost halfway through the year at this point. Oh, well, not quite. There'd be halfway through the year, so we're getting close to being halfway through the year at that point. All right, so that's the history of the universe. Now, to go through the planets individually, Mercury takes only about 3 Earth months to orbit the Sun. Therefore, it is considered the fastest of the planets. It's named after Mercury, I believe, is the Roman god that was very, very fast, or some kind of Roman figure that was that carried information, I guess, back and forth between the different gods or something like that. Oh, there it is, right there. Because it was named after the Roman messenger god. Okay. See, I made this fall of 2019. Mercury was also the god of travelers. Then this would be the symbol for Mercury, nearest to the sun. In Greek myths, Mercury was Hermes, the winged messenger god. Venus takes about 7 Earth months to orbit the sun. Named for the Roman goddess of love and beauty, also known as the morning star and the evening star. The reason for that is that it follows the sun in the sky. So here I got Mercury. Here, let me do this. Okay, so I'm centered on Mercury. Right there's Mercury. Can't really see it too well because of the phase it's in. If we go out far enough, there's Venus. There's the sun. Okay. Now let's stay centered on Venus. Let me turn the Earth back on. So there's the Earth. We don't see it because it's down below probably. If you go back further enough, we can see the Earth. There's the Earth. Okay, so let's get it so we can see the Earth. Now, as you can see, Venus is going to set before the sun does. That means that we will not see Venus tonight. It won't be in the sky. But watch what happens here if I go ahead in time. So I'm doing the speeding up time. So Venus sets I watched the next morning. Probably slowed it down too much. There's Mars. Tomorrow morning. Capella's rising tomorrow morning. There's Venus. Okay, Venus, we'll see it. When the sun comes up, the sun's going to overwhelm Venus. So in this case, Venus would be the morning star. Okay, there's Venus right there, the morning star. It's just rising above the Earth's surface. So as long as the sun is still kind of underneath the horizon, so tomorrow morning, 5:39 a.m., if you want to get up that early, you can go out, you could probably see Venus. But what's going to happen a little after that? Now the sun comes up, and the sun will overwhelm Venus, okay? You won't be able to see Venus then. All right, so that is why it's called the morning star or the evening star. In this case, right now, it'd be the morning star, okay? Because you see, I don't have the atmosphere on. If we put on the atmosphere, boom. So you can't see. There's Venus right there. You can no longer see it. If we go backwards in time with the atmosphere on, let's go back to. Where you can see Venus disappeared. With the atmosphere on, you can see Venus right there. You can see it. You can see it. But the sun's coming. Oh, Venus disappeared. There's the sun. The sun overwhelms it. So we can see it for a little short time. We'll be able to see it for a little short time tomorrow morning if you want to get up that early. Okay. Let's put it back to where it is right now. Alright, so let's go back to PowerPoint. So that's why it's known as the morning star and the evening star. Oops. Then this is the symbol for Venus. Venus may have been named for the most beautiful deity of her pantheon because it's shown the brightest of all the 5 planets known to the ancient astronomers. Venus is the Roman counterpart to the Greek god Aphrodite. And there's the symbol for Venus. Mars, 4th planet from the sun, takes about 22.5 Earth months, almost 2 Earth years, to orbit the sun. Carries the name of the Roman god of war. It's got that red color, kind of like the blood color of blood. So that's why they thought it was like the god of war. The Greek god of war was called Ares, also known as the red planet. Okay. And there's the symbol for Mars. Perhaps named after the god of war due to its red color, similar to the color of blood. Mars' 2 moons, Phobos, panic, fear, and Deimos, terror, dread, named for the Greek mythological twin characters who accompanied their father Ares into battle, though not discovered until 1877. So they're very small moons. So we go back over here to Stellarium, and let me turn off everything. Turn off the land, turn off the atmosphere, and then come over here and locate Mars. This is just Stellarium. It's on my channel for the tutorial for how to use it. So I go Mars, and then there's Mars. So we go in, go in, go in, go in, go in. There they are. There's Phobos and there's Deimos. And there's Mars right there. Okay, and you can look at time going ahead. You can see how they'll move on orbit Mars, back and forth over time. Okay, so let's go and put it back to normal time. So that's right now. All right. Oops, where's okay, so this is where we're. Jupiter takes about 12 years to orbit the sun. The largest planet in the solar system, named after the king of gods in Roman mythology. There's the great red spot. That's the big, huge hurricane that's on the surface of Jupiter. Earth could fit in that. That's how big it is. There's the symbol for Jupiter. Ancient Greeks named the planet after Zeus, the king of the Greek pantheon. And of course the Romans, they stole the Greek gods. They stole basically their culture, and then they just renamed stuff so to make it their own kind of. So Zeus became Jupiter. Over 1,300 planets the size of Earth could fit inside of Jupiter's volume. So a lot of plastics, like 1,400 something, I think. Saturn is the farthest of the planets known before the invention of the telescope. So before the telescope, you didn't even know there was a Uranus and a Neptune. Named for the Roman god Saturnus. That I'm sure I looked that up. the god of agriculture and harvest. And there's a symbol. According to the myth, Saturn introduced agriculture to his people by teaching them how to farm the land. Saturn is the equivalent to the ancient Greek god Kronos. I don't know if that's... Maybe I just gotta... I don't know. I'm going to leave that for now because I'm sure I would have looked that up when I did this. That may be wrong, but I'm not 100% sure, so I'm not going to change it right now. Okay, Saturn is the equivalent to the ancient Greek god Kronos. Uranus and Neptune, unknown to the ancients. Okay, you had to use the telescope to find these. Galileo may have discovered Uranus because he made little notes in his journal about something he was looking at that was not moving with the background stars. In other words, as seen from Earth, all the stars, everything outside of our solar system moves together because of Earth's spin on its axis. That's it, all right? And they're all going to move together because Earth's spin on its axis is constant, doesn't change that much. And they're all going to look the same place in the sky. But things that are also orbiting the sun in our solar system, they are going to move relative to the background stars. And Galileo found something that was moving relative to the background stars. He covered it for maybe a few days or something like that. Then he left it alone. And so he may have discovered Uranus. They think he may have, but he didn't really write it out, so he doesn't get credit. Neptune is the god of the sea, Greek god Poseidon. Okay, so now this is, okay, now we're getting back to where the book was. No, we were where the book was. This is where the book was here. So this is how the universe on a large scale in your textbook. Okay, so basically there is the Andromeda Galaxy, M31. These are a cluster of galaxies, okay? So you can see there's these different spiral galaxies and so on. Hold on a second, let me do something. So in Stellarium, you can find deep sky objects. So it's this right here. See, deep sky. If you look over here, it says deep. Where is it? Deep sky objects. See what I'm. See, like this one right here, what it's looking at right now. If I turn that off, it goes away. There, it's not there anymore. So I turn it back on, it comes back. So you can click on it. I already have. So it's an active. It's a galaxy, active galaxy, and it tells you a bunch of information about it. You've got another one right here. Here, this is another galaxy. You've got one down here, another galaxy. So they're spread out, and these are just the ones we can see. So let me just go on that one and get up close. Center it. See what it looks like when we get really close. Here we can see it's a galaxy. Look how far away it is. It's 65.566 million light years away. So the light you're looking at here started towards Earth 65.5 million years ago. Okay, and so you can try the other ones too. So that's how vast things are. Okay, and remember, this is just the observable universe. You got this one here. This one that's got a name with it. Galaxy. Okay, so center on it. Let's go in for a close look. Look how far away we're going. We're leaving all the other stars, and that's a weird looking galaxy. It's as close as we can get. So you can see there's different types of galaxies. I have to look up that one to see what it's so different for. So there's a galaxy here. Center on it. Center on it. What's going on here? Get out of here. Center on it. Oh, see, that's so far away we can't get any closer than that. Okay. So that gives you an idea of the vastness, all these galaxies out there around space. Okay, so how big can things get? We've got the Andromeda Galaxy is about 220 light years wide. Okay, that's how wide it is. So light that starts off over here is going to take 220,000 years to get to this side. That's how vast and how wide it is. Okay, the observable universe is about 93 billion light years across. It takes 93 billion years for light to get to from one side of the universe to the other, basically. The universe overall may be as much as 150,000 light years across. That's not right. 150 million light years across. Yours is going to be wrong. It's going to be. It's. Hold on. Okay, so unfortunately, right now I'm uploading another video onto YouTube for my astronomy lab. Here it is, right here. It's only 20% uploaded. It's going to take another 2 hours and 12 minutes. And basically, when I'm doing this, I can't do anything on the internet. I try to look up exactly how wide the universe is, and it just tells me page can't be found because I'm taking up too much bandwidth uploading the video. So I don't know exactly what this year is, but this I think it's 150 million light years. 150,000 or this is 93 billion. So 150. Okay, I'm just guessing. I think it might be 150 million. Maybe I have need three more zeros in here. Okay, this is not a right number. I'm certain. Okay, because obviously 93 billion light years is what we can see. That's the observable universe. That would what we can't see. If we include what we cannot see, that'd be a much bigger number than 93 billion. Okay, it just makes sense. So this is not a correct number, and I was going to look it up, but I can't because I'm uploading another video right now. Okay, so we talk about how small things, how big things can get. And we have how small things can get. So I've included a picture showing two people and a meter stick to give you an idea. If you're not familiar with the meter stick, you don't want to have one handy to look at. What about the size of a meter stick? Okay, now if we divide this thing up, this thing here that's like, maybe a little more than half the size of an average human being, all right, well, we can divide it up 1,000 times. So this is be like 90 centimeters right there, or about 0.9 meters, and then there'd be a millimeter right there. So that's 1,000 of these little divisions in a meter stick. So there are 1,000 divisions on a meter stick called millimeters. So there's a millimeter. Divide each millimeter 1,000 times, we get micrometers. That'd be 10 to the minus 9 meters, or 10 to the minus 6 meters. Divide each micrometer up 1,000 times, now we get nanometers, 10 to the minus 9 meters. Okay, we are just now approaching the size of an atom. So you take a look at that little tiny division there. Okay, and there's 1,000 of them along here. Take one of those 1,000 divisions, divide it up 1,000 times. We're not even at the size of an atom yet. You got to imagine taking one of those little tiny divisions, and there's 1,000 of them in this little distance right here, and divide that up 1,000 times, and now we're getting kind of close. We're down to 10 to the minus 9 meters, and I think you got to go to 10 to the minus 10 to really have the size of an atom. Okay, so that's how small things can get. Here's all the elements in the periodic table. Hydrogen and helium are primordial, but all these other ones, all the ones we're used to, all the ones we rely on to exist. We've got oxygen over here, take a look at that. Your neon signs, your Silicon Valley, you've got your smartphones in there. Your smartphones couldn't exist if you didn't have silicon, because that's why it's called Silicon Valley. They use silicon to make these wafers, and they dope them so that they can get transistors, and they can shrink the transistors down very, very small, and they can put it all on your smartphone, and you can do stuff with it that you benefit from. Okay, so anyway, you got the gold. Basically, gold is Au, there's silver, there's copper, Au, gold, Ag, silver. All those precious metals are right there, and they all came from a star that blew up. So it would have blown up over 5 billion years ago. It would have been synthesizing all these elements in order to try to survive. It would reach iron, Fe, iron's right here, and that's the end point. It can't make any more energy through fusion anymore. So now out of desperation, it makes all these other ones trying to survive, but it's not going to work. It blows up, goes supernova, spews all these elements out into space. They kind of come together in a big cloud. The big cloud starts to shrink, 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 and it makes the sun in the center. It makes all the planets like the Earth orbiting around the sun. Okay, so that's how we got to be, our solar system got to be. Okay, okay, that's it. So how big things can get, how small things can get. So there's everything. This is all of Chapter 1. So there was how large things scale, small scale. We talk about the galaxies, and then down here they talk about very small things. And they talk about the atom. Oh yeah, there's one more thing here. Um, hold on. Okay, the other thing I was thinking of was going to PHET and looking at this thing where we build our own atoms, and we're not going to be able to. Here, it's here. Do I have it? No. See, we're on the internet to do these things, and so because of this. Okay, because I'm uploading another video to the channel for the astronomy lab, I'm not going to be able to do this. Maybe I'll try to come back and do it. Let's see here. Can I do this? No, I don't want to close that. Oops, that'll stop recording or uploading. So I think what I'll do. Let me do this while I think what I'm doing. Okay, the other video is finally finished loading, so now I've got internet access again. So what you do is here, I skipped ahead. You just go to Google, you put in PHET, something like this should come up, and then click on physics for what we're about to do. Remember, we're talking about small things in the universe, and we're going to build an atom. So you simply click on it, hit play, interactive simulations, build an atom. Alright, so this is the outskirts of the atom. First of all, what we'll do is we'll add a proton to it, and we get hydrogen. It's a plus ion because that's a plus hydrogen nucleus. Okay, it only has one proton. So what we do is we add an electron. Now it's a neutral atom. It's neutral hydrogen. We add another proton. We've got helium. Add an electron. And now we've got neutral helium. It went over there because electrons, remember, repel each other. And then if we put in another one, we're going to have lithium. And this is going to be unstable lithium. That's why that thing's bouncing around. The reason it's unstable is because we got to add neutrons. Still unstable, still unstable, still unstable. Oh, it's stable 3. Okay. I think it's more stable than 4. It's still stable. If I put another one in, it becomes unstable again. So we get one of those out. Okay, but we have 3 pluses and only 2 minuses, so let me add a minus to make it back to be neutral. So that's basically how these atoms work. These little tiny building blocks of protons, neutrons, and electrons. Let's make this a neutral one. And then make it neutral. And we go next up, we got beryllium. Let's just skip up to one that's kind of important for life, carbon. This would be unstable carbon. So we put some, I think that only has, is that a 1, 2, 3, 4, 5, it has 6, okay. It has 6 neutrons as well. That'd be carbon 12, 6 protons and 6 neutrons. And we can't go too much further because we're going to run out of, there's nitrogen, that's important for life. There's oxygen, next one up there on the periodic table. That's important for life. Okay, brush your teeth, put fluoride in your toothpaste. You also have to have, we have to actually add another one to make that stable. There you go, that's stable. In other words, they break up. If this thing's shaking around, that's not going to be stable, it's going to break apart. The last one we can get to is neon. Neon will be stable. You can keep adding neutrons to neon and stay stable. Now it got unstable, that'd be unstable neon. Okay, so I think we have okay, this is where we were when I shut down because I couldn't do anything over the internet. Okay, so this is where we were. This is how small things can be in our universe, and then this is how big things can be in our universe. And I think we've probably covered all the questions. We've got these. This is the Neptune. Oh man, this looks like it's already finished. Alright, I'll leave it here. So I'm going to come up with a quiz for you guys to take Tuesday morning during what would be our regular class meeting. And I'll stick to these questions here, but I want to add, for the next one, I'm going to add some questions. It doesn't look like I did anything with how small or how big the universe can be. So I'll try to stick to this stuff right here for the quiz on Tuesday morning. Make sure you study the PowerPoint we have here. Okay, and then probably I'll have another video up this weekend, hopefully. But the quiz will just cover what we have on this. I'll use this as my guide to what to put on the quiz. Okay, so I'll talk to you later, and good night, good morning, good evening, good afternoon, whatever it is. So I'll talk to you later. Good night.